In society today, it's nearly impossible to avoid the concept of metabolism. People may complain about having a slow metabolism or brag about having a fast metabolism that supposedly allows them to eat anything they want. But have you ever wondered what exactly this means for you and your health? Calorimetry is the measure of absorbed or emitted heat and is used to assess metabolic rate, which is the amount of energy used per unit time. It has been fundamental for understanding of metabolism in health and disease and offers a way to quantify the heat released through aerobic and anaerobic metabolism. Metabolism can be affected by a variety of factors, including mitochondria's number and size, enzymes, and substrate availability. A calorie is defined as the amount of energy it takes to raise the temperature of a kilogram of water by 1 degree Celsius. This energy can be measured in a multitude of ways. When you're exercising, you utilize nutrients and oxygen and output heat, carbon dioxide, and water. While it is possible to measure the oxygen use and carbon dioxide release through indirect calorimetry, it is much more accurate to measure the heat itself through direct calorimetry, which is often considered the gold standard for measuring human metabolic rate.
The principle behind direct calorimetry is relatively simple in that it utilizes the first law of thermodynamics. The first law states that energy cannot be made nor destroyed, but can be converted into other forms of energy. As humans, we convert several different types of energy into useful and non-useful forms. Food begins as chemical energy and is stored in the body in the bonds of macromolecules in ATP. However, when we move and exercise, we convert this chemical energy into mechanical energy. Ultimately, our body converts this chemical energy into heat, which we are able to quantify and determine metabolic rate by using the methods of direct calorimetry.
Direct calorimetry uses the concept of heat transfer to measure the temperature change in a closed system. The combustion reaction within a calorimeter must be adiabatic, meaning that all of the heat produced must be contained and cannot be lost to the outside environment. If not, the amount of heat measured by the calorimeter would be less than what was actually generated by the reaction. In a traditional direct calorimetry setup, the subject is placed in a virtually closed system, often a chamber, and is asked to perform an exercise. The heat the subject emits is then absorbed by a water pipe system that runs through the closed chamber. The difference in temperature, measured with a thermometer, before and after the water runs through the chamber is used as a measure of energy expenditure and therefore metabolism. The number of calories burned can be directly calculated based on the increase in temperature per kilogram of water that runs through the pipes.
As we have stated, direct calorimetry measures the heat generated by a subject within a constant volume by observing the change in temperature of the water, delta T, that is running through the pipes in the chamber. This change in temperature is a direct measurement of the amount of energy, or calories burned while completing the given task. This equation expresses the change in internal energy, and therefore emission of heat, and is defined as mass times the heat capacity constant times the change in temperature. The heat capacity is the amount of heat required to raise the temperature of the system by 1 degree Celsius, and for water, this constant is equal to 4.184 joules per gram times degrees Celsius.
Despite the accuracy of direct calorimetry, it is actually used very rarely. It was originally used as a research tool, measuring things like basal metabolic rate, the amount of energy used at rest, but it has grown relatively unpopular due to its expensive and complicated nature. It is nearly impossible to create a completely closed system and requires a great deal of expensive equipment. In fact, there's only one known operational direct calorimeter, the Snellen calorimeter, located at the University of Ottawa Human and Environmental Physiological Research Unit, shown here. The introduction of this new technology allows a rapid response time for evaporative heat losses and a higher level of precision, which was a major advancement from previous direct calorimeters. Still, this method of direct calorimetry is generally not preferred due to high cost and relatively small size of the chamber, which restricts the type of activities that may be performed and studied.
While direct calorimetry is considered the number one method for accurately quantifying heat production, indirect calorimetry is much more commonly used to measure rates of energy production. Indirect systems today are able to make continuous measurements and have even been made portable to allow for measurements to be taken under varying conditions and during a large range of activities. However, in this method, metabolic heat production is determined indirectly by measuring the difference in oxygen and carbon dioxide contents between expired and inspired air. This observation allows for the assessment of oxygen consumption, or VO2, and carbon dioxide production, which are then used to calculate the respiratory exchange ratio. This ratio can then be used in the calculation of energy expenditure using the caloric equivalents for macronutrients. While this method may prove to be quicker and more efficient, it has its limitations in its accuracy. Although energy expenditure can be equated to heat production at rest, it cannot during exercise because approximately 20% of energy produced goes toward performing external work.
Overall, due to high costs of operation and maintenance, practical use of direct calorimeters has become limited. Only one research institution still uses a direct calorimeter today, but it still continues to be important in understanding metabolic processes in healthy and diseased populations. These direct measurements of metabolic rate are useful for defining the amount of energy necessary to perform different exercises and across varying catabolic situations. Direct calorimetry has also been used to study how sex, aging, chronic health disorders, and severe burns influence human thermoregulation. Despite its limitations, direct calorimetry has advanced our understanding of energy expenditure and whole body heat exchange, and has opened the doors for a variety of new methods for studying human metabolism.